Hello everyone, video 4 of module 7. In this video I will show you how to design steel elements. So first thing we need to do, we already set the parameters for steel elements and there's nothing special that we need to do in terms of other specifications for sections, and we set the standards and everything last time. So we start design just by click on steel design button. The user interface is very similar to concrete. We will go through them one by one and we check different type of steel elements together: beams and columns and braces, struts, and also composite beam. Okay, the design is done. I just coming here and select by material all steel elements, select properties, material properties, and I use this, select show selection only, and we have just beams. So see what is showing here. Generally when you design a steel structure, what you can see here is the ratio, which if I come here in design info, you can see PM ratio. So it's mentioned here based on color and values, but initially what SAP shows you is the section size and just the color for PM ratio. So let's zoom closer to a part of elements. Okay, so here we can see some elements are blue, which is utilization of this ratio is very low. Some elements are over stress, but are they designed correctly? We need to check here. So let's start from columns. So I'm coming this way, which is a bit more clear for you. So I'm selecting this column. Again, I right click and see just showing me that this element is over stress. So let's check the details and see what do we have here. So here you can see this is designed based on AS 4100, which is Australian standards, and he's mentioned some information about the critical load combination and also how it was designed. The design type is column, frame type is the sway frame, and here is mentioned that the length is 5 meters. So yes, the length is 5 meters, but you need to see the height was used in the design, because one side you have cladding, and for cladding you have girts, and those girts are called form sections like a C or Z, and they can create some lateral stabilities. So here when you come down, you see the major bending and minor bending, both lengths are 97% roughly. So this ratio coming from the rigid zones that you have for top and bottom part. And then what is your sway KE, which is 6 and 7. And also when you come here to axial load, you can see the basic factors are high. Why the K factor is 6 or 7. The K factor, actually you have brace in one side and you have frame in the other side. So in the major direction you have moment resisting frame, in minor direction for the column you have brace. But before going through these, what we need to check is the orientation of the elements. So what I do here, I get back to undeformed shape. I have two ways to check this. Either I can come to check the local axis and check the orientation of the section. So this is correct now. This is axis 1, axis 2, and axis 3. So the strong direction of the section is the way I want. So axis 2 is always showing the axis along the web. If I come here to define sections and for example show this one. You see this is axis 2, and this is what I want to see here. The other option is using extrude, that if I back to this normal situation, generally when I press extrude I should be able to see the actual shape of the frame, but for some reason it's not working, but we know that the orientation is correct. So along the major direction of the moment, the length would be exactly the effective height of the column. But for the minor direction, because we have gears, we need to adjust the length ourselves because we haven't modeled those elements. SAP doesn't understand. So this is our job to update this. So let's back to the element PMM ratio. We have few options here. I will explain them. Let's finish this and then I will get back to this. So here if I right click, I can see this element is overstressed. I know the reason. So I'm coming to override and update some of those factors to make it right. So here we have on-brace length ratio measure. So on-brace length ratio measure is correct. So SAP detects top and bottom beams and there is no other support at mid height. So I'm happy of what SAP determined as on-brace length for major direction. For minor direction, I have a wall cladding, and to support the wall cladding I have some gears, and those elements can create lateral support. The space between gears are something around 1.2 meters. So this length is not correct in minor direction. So what I need to do, I need to see what's the ratio of the effective length to the total length. The total length is 5 meter. A space between gears are 1.2. So 1.2 divided by 5 is 0.24. So I need to come here for minor and put here 0.24. So here the effective length factor, K factor, I need to check it. So SAP shows me 6 and 7, which is not correct. Even if we have very long span beams and effective of the stiffness of beam is not too much, worst case scenario you have a cantilever column, and cantilever column K factor is 2 or 2.2. But because here we have a moment resisting frame and the spans are reasonable, I just put it something around 1.6. We need to calculate the stiffness of the element and provide it properly, but 1.6 is roughly reasonable. For minor we have vertical braces, so actually what we need to put here is 1, and the same here for major, for sway, so it's 1.6 and 1. And there are other factors. You need to check the parameters based on your local standards. Some of them can be still edited, but even if I accept those and press OK, you see this ratio come to 0.154, which is very smaller than 3.2, so it's roughly 20 times of this. And if I press OK, I can see this one is changed. You don't have to do them individually. You know that this condition is for all columns. So what you need to do before doing the design, you need to select all columns and then come here to view, revise, override, and you have exactly the same menu here. You can update these parameters for a certain group of members, press OK, and it will be saved. And then when you design it, all of them will be designed properly. So this is for columns. Before I go through design the beams and other members, let's see what we have here in our menu. So view preferences, this is for the standard that we checked at the beginning when we changed our standards. We discussed about that. The next one, view, revise, override, I just explained you. Select design groups is a useful tool to select a typical section for a group of elements. For example, you want to design your roof frames. You can add all your columns to one group and all the beams to another group. And when you add them here to design group, SAP will automatically select the same section for all those elements in that specific group. And this is a useful tool to make the sections typical, because we don't have different sections of columns on each frame. This is not practical. We need to see if we can, for example, have two types of frames, because fabrication would be very expensive if you want to choose different size of columns and beams for each element. So you need to optimize everything. It's not just a matter of weight of steel or section size, is a matter of the ease of fabrication and erection, and less mistake in especially erection if you have different size of columns. The other thing we have here is the design combo that we discussed before. Displacement target. You can have a displacement target. You can mention, for example, for each load case, what is the maximum displacement you can accept, and based on that, if the displacement is more than that, SAP will make it as a red mark element. The other thing we have here is time period target, which is not our discussion for this session. And then this is the icon for the started design that we used it before. Then interactive steel frame design. I'm not generally using this, but if you select any element, if you change it, SAP automatically redesign it. And display design info. Here the first one we use PM ratio and color and value, so you can see the color rate between from 0 to 5.7.9 and 1 and more than 1, and you see this color code is actually consistent with the ratio that we have here. The other options we have here is with shear ratio values. So you have a color for PMM, you can see if it's okay or not, and then you see what's the shear ratio value, and these numbers are very small. You can see in the two direction, so direction 2 and 3 and what's the shear ratio. So we utilize 8% of the shear capacity of this beam, for example, in 2 direction, and less than 0.1% in 3 direction, which is the minor direction, and it's normal because you don't have any shear in weak direction or minor direction. What else we have here in display design info is PMM ratio, color, and no value. So you just see the color. If you press it, you see just the color code. Sometimes because the elements are too many, if you have the text is not very clear, but the color code here shows you which element is overstressed. So for your report could be useful sometimes, depends on the level of information you want to prepare. And identify PM failures again, so when you select these, SAP shows you that which elements are overstressed, and that's how you can figure out. Sometimes that could be overstressed due to shear. So if I press this and then come back to this one, display design info, and mention shear failure, you see, you can see the color. So PMM color is always here. You can see the color regardless of the overstressing due to shear or not. So don't be confused with the color. Color is not an indicative here. So what do we have? If we come here, so this is for all failures. So if you do this, you see it mentioned that due to flexure or shear or other, all of them are clear here. Just give you some idea that what's the reason of the failure, then you can go and track it. So this is for columns. Let's finish elements due to axial load, and then we will go and check the beams. So the other option I would like to discuss with you are braces. So let's get back to PM ratio and values, which is more understandable for us. So I'm zooming here a little bit for these two braces, and I can see here this ratio is absolutely high. So if I click on that, it's literally overstress. And why is overstress? I need to again check what's happening. So EQY is the critical combination, and I'm coming here to details, and I see that it mentioned that the element is overstressed and buckling due to axial load. I can check here what it shows me. So the length is 7.8 meter, which is the full length of the brace from this joint to this joint, and then it gives me the other information. What's the shape we chose here? Currently it's showing me 125 by 125 by 10 equal angle, single angle, but generally for vertical braces, kind of T-shape or star shape is the shape that is more popular for double angle. Let's have a look at the other ratios. So the K factor is 1, which is correct. Here you need to check your L factors. So L factor, if you remember, we didn't auto mesh the braces because we didn't want to have half on both sides. So what do we have is actually in plane buckling. When you have a connection here, you just have half of the length, but out of plane buckling, that will be a little bit controlled and stiff by the lateral bending stiffness of the other brace. So it's not half because this is not very strong. Generally the factor we use for out of plane buckling ratio is something around 0.7 to 0.8. So I will choose 0.75 for the length factor. Both K and L give you the same result. So what I will do, I'm coming to override, and here I need to see major and minor because this is axial load. You can put major and minor here, but actually you need to check the axis. But anyway, the result would be similar for equal angle. So I'm coming here and I mention on brace length ratio. For major, I will check it 0.5, and here I will check it 0.75. Sometimes people are conservative, they go for 0.6 and 0.8. You need to see your local design procedures and recommendations, but 0.5 and 0.75 is almost okay. Then the K factor was determined 1 by program, so we leave it as it is. Now the ratio is still high, so here was very high, but it still is high. It's coming to 14. It still is not acceptable. That means the load we have here is a very big load. So you see here that the axial taking about 96% of the capacity just for axial. Then you have bending major and minor, and those bendings coming on board, and you need to see why you have bending here and if you can reduce those. It's coming mainly due to buckling, but if you use a stronger section, then you don't have such an issue. Currently we don't have element stronger than 125, but if I override the section here by another section, I'm just choosing to show you the difference. So I'm coming to 180 UV and see what's the result. So it's still showing weak result. The reason is the major direction and minor direction are different. So here if I come here and put major direction 0.75, that means I'm rotating the UV, and put this one 0.5, see if it helps or not. Coming to 0.68, you see how much it changed. So if I press OK, now I can see it's alright. So UV is not a good section for such a brace. For very strong bracing, for heavy industrial structure, we're going for a UC section or very strong welded plate section, I shape, with thick flanges and thick web. But here it's just simply a double angle or double C section would be okay. I will leave it as it is. I don't want to go through trial and error and finalize our design. I'm just showing you guys what needs to be done. So for brace, what you need to always check is the effective length ratio for out of plane and in plane. The same for roof brace. The difference between roof brace and vertical brace is generally roof braces are designed for tension. That means you need to define those braces as tension only member, and you need to do nonlinear analysis for tension only members. That we don't have this license at the moment, so we cannot do a nonlinear analysis. But if I come here and check, you see the major issue is again buckling. So you see the N star is the total axial load you have, and those are some minor moments you have. And then you come here at the bottom, you see the capacities of the moment, which is here is acceptable, but what is the capacity of axial? The capacity of axial in tension is good, in compression is very close, and that's why when you have buckling, suddenly this ratio increase dramatically. Let's change these factors and see how much it can help, but it may not help too much. Let's see how we go. If I come here in override and check on brace length ratio, major is 0.5, and here in minor, which is out of plane, 0.75 could be a bit high. Sometimes they use a hanger and connect the braces to the purlin, so I just put here 0.5 for this specific one, and I assume that I can have a good connection here, like a hanger or any element that prevents this braces of buckling out of plane, and I can see it's coming to 0.26, so it works. So those are for vertical and horizontal bracings. Struts are pretty similar, so if I just zoom out a little bit, so you see you have some struts here. For example, if I come here, I see those struts are okay. So if I choose this strut, you see this is a hollow section and the capacity is good. If you check the details, you see the lengths are almost close to 1, back to the rigid zones, and the factors are correct, and the slenderness ratio is less than 200, which is okay. You can see here what's the maximum axial load you have in the strut and in which load combination you have it, which is EQY5. And then when you come down, you see the moments are nothing, and the moment capacity here is shown. This is based on, again, Australian standard. You need to check your local standards and the factors you have. And here for axial load, we have 28 kilonewton roughly axial load, and the capacity for tension is 242 kilonewton, and for compression is 81. So the ratio you see above, which is almost about 0.4, coming from this 28.5 divided by 81.4. This is how it's gonna be calculated. And as I said, this is the tensile capacity, and also we have shear, but we don't need them. Again, the facility you have here for printing is pretty similar, and is mentioned here what type of a standard you use, and this is a summary that you have for this design. So those are for elements due to axial load. Let's have a look at the beams.